Good afternoon, everyone. So you get two presentations for the price of one. I'll first be talking about some of the work that we've been doing at TU Delft, working on the aerodynamics of meteorites. This is one of the very first studies that we've done. So I'm actually presenting on behalf of my my master student, Saisaran Adoro, and he defended his MSc thesis already, I think, more than a year ago. But we've been sort of interested in understanding how sort of the shape properties of meteorites might actually influence the aerodynamics. And there are some considerations that we are looking into. I mean, if we dive into the literature, we can see a lot of cases where they are basically describing that the location where meteorites are found are actually deviating from sort of the predicted impact points based on the dark flight modeling. And a very common argument that people are providing is that it's due to either the meteorite shape or certain aerodynamic processes that take place during the dark flight. Now, at the same time, we don't have a lot of experimental data to understand the processes that are taking place. And if we consider sort of the flow regime, it's also in sort of the subsonic regime, and the sort of the sparse wind tunnel experiments that exist actually focus more on the higher end, the very high hypersonic types of wind tunnel experiments. So for us, there are some interesting boundary conditions that we wanted to focus on. So especially the lowest part of the atmosphere of the dark flight, so really the 10 kilometers and lower. It's really the regime where we go into the sort of subsonic flight regime, where also the meteoroid resides for the longest in terms of the amount of time relative to other phases. So this is quite an interesting sort of domain where we could potentially tailor wind tunnel experiments to understanding sort of the aerodynamic properties and the aerodynamic behavior. So there's a reason to focus on the dark flight of these processes, because in the end, if we are capable of understanding these properties a bit better, then potentially we could try to refine our strewn field predictions. And we've seen some very nice talks also yesterday evening about how important those shape and aerodynamic properties could be in the location, especially the strewn fields that are being generated. Now, of course, the dark flight itself or the predicted impact points in the strewn field, they depend on a number of properties. One of them is the wind profile, and tomorrow we will have a nice presentation also by Felix, who will be talking a bit more about the wind data. And here I will focus primarily on the meteoroid shape and also the aerodynamic effects, and especially what we can learn from them using a number of interesting techniques. So for us, the focus has been on a particular case study, which is the Broek in Waterland chondrite that was found in January 2017. And this was quite an interesting case study, because if you look at the shape of the meteorite, it is a very asymmetrical, very contrasted shape. So it presented to us one meteorite with sort of a large variety of shape and other properties that we could test in the wind tunnel. Now here you can see sort of the top image that's actually a render of a 3D model of the meteorite. So we were able to document the shape of the meteorite before it was sampled by other colleagues for the sort of detailed petrographic analysis. So it means that we have the original completely fusion crusted meteorite available for these wind tunnel studies, for example. So the present day photo, you can see there's a very nice cutout of the interior. But of course, this particular model would not give us the actual aerodynamic properties, because, well, frankly, there's a bit missing of the rock. Well, I want to talk you through, well, 3 steps that Saisaran did in the wind tunnel project. So I want to take you first to the first step of his project, where he looked at sort of the drag properties of the meteorite with just a one-on-one scale model that we generated. Then in step 2, we are going to take a look at how these aerodynamic properties might actually vary with altitude based on some of the experiments that we performed. And then in step 3, we'll look at some of the implications, and somewhere along the way, we'll talk a little bit about rotating meteorites and some other very cool, fancy stuff. But I think one of the key innovators that we were able to leverage in this project is that we were able to generate a very high resolution 3D model of the meteorite using photogrammetry. In my next presentation, I'll talk a bit more about that. But the very interesting thing is that because this one was scaled to real world units, we could actually measure a lot of physical properties. So we could basically determine cross-sectional areas, we could measure the characteristic length, and of course, for the wind tunnel, we could just print meteorite after meteorite that we needed for these various orientations in which we wanted to measure the meteorite itself. So on the right-hand side of this slide, you can see sort of the printing process. This is actually a model that we used later on, so it's a larger model that we used for step 2 of the process. But yeah, we can actually go from the photographs all the way to a 3D printed, real sort of test article for the wind tunnel itself. Now, this is sort of a picture of the wind tunnel. So here you can see sort of the 1-on-1 scale model mounted on a post rod, and it's mounted or attached to a 6-component force balance. So this is what the colleagues usually use at the aerodynamics department to measure all sorts of aerofoil shapes and model aircraft and so on. So they were a little bit puzzled when we came with this very odd-looking potato-shaped type of object that we wanted to put in the wind tunnel. But at some point, they were getting very interested and enthusiastic. So it was really sort of a new thing that we're trying out that also they enjoyed very much. So in this setup, the wind is coming from the top to the bottom, so to say. So this is sort of the flow direction. And then depending on sort of the test protocol, we sort of change the orientation of the meteorite in various directions. And that's what you can see in this particular slide. So just to involve you a little bit into the aerodynamics. So in this case, you have to pretend that you are the wind. You have to, ruffle your hair and whatever, but the wind is moving from you into the screen. So basically what you are seeing here is sort of the leading edge, the orientation of the meteorite as it was facing the wind flow. So when I'm talking of various phases or various orientations, you have to imagine that these are sort of the contrasting shapes. So you can see that, for example, shape number 2 and number 6, these are the parts of the meteorite with a secondary fusion cross. So they're a little bit more jagged, a little bit more straight surfaces compared, for example, to orientation number 5, which is very nicely smoothed out and a bit more aerodynamic, if you will, compared to some of these other objects. Now, what we found in the very first step is that if we subject the meteorite to the wind flow, we can actually see that there's a large variety of these aerodynamic properties. So depending on the orientation, we can measure basically the lift force. So if it's being pulled up basically by the air or being pushed down, if there are effects that are basically pushing it sideways, and in this way we can get sort of an idea of these sort of side forces, drag forces, and also these lift forces. Now, of course, fully, as you might understand, phase number 6, which is sort of the very flat plate that's facing the flow, that one actually has the highest drag coefficient, whereas in other cases you could see that those forces are very different. So this sort of spiderweb diagram really illustrates well that these aerodynamic forces are definitely not something that you can just generalize depending on the shape. So if you assume a very nice spherical object and the real world is something different, these forces will actually differ in reality as well. So it's sort of the evidence for sort of the intuitive feeling that we might already have. So taking step number 2, this is really where the data from the very first experiments came into play, because moving into sort of the flow regime, if the object is falling from higher up in the atmosphere towards the ground, so across a couple of kilometers, we needed to scale our wind tunnel experiment. So one way to do that is using flow similarity. So since we can't change the atmospheric pressure, we can actually change the wind speed and the size of the object to get into the same flow conditions, the flow regimes, to perform experiments where those results would also be valid for what the real meteorite would be expecting or experiencing when it's falling towards the ground. In this case, we use the scaling factor based on the drag coefficient. We need to scale it up to about 1.75 times its original size, and we could do these wind tunnel studies again to see what this would give us. Now, the interesting thing is, I don't want to get into too much detail, but we did see that there is sort of not a sort of a linear behavior. So we can see that there's a variation in height of these various aerodynamic forces. So it means that if we actually have an object that's falling towards the ground, we can see that these forces might differ as well. Now, on a little bit of a side note, of course, this is something that is also being challenged by sort of the aerodynamic stability of the meteorite, because we can imagine that the meteorite might be tumbling, but it could also be in an oriented fall. So we did this sort of funny looking rotating experiment where we allowed the meteorite to rotate around one axis. And what we found there is that as soon as it's rotating, it's basically negating or averaging, nullifying, whatever you want, the force balance. So it means that as soon as the object is rotating, you actually sort of lose the preferential side force, aerodynamic side force of an object falling towards the ground. So depending on whether an object is falling in sort of a semi-oriented, stable fall, will actually mean that it will experience more aerodynamic side forces that would affect the ultimate impact location within a strewn field compared to a non-oriented one. So in this case, that's something to be considered. Now, to put it a little bit into perspective, if we look at sort of the range of these aerodynamic properties, what are the consequences once we have a meteorite that is falling? So we made use of a dark flight simulator, the PyDAT from Bettonville and Bettonville. I think they presented it the previous IMCs as well. And we basically plugged in these parameters that we got from the wind tunnel experiments, also those that we found in literature, and we set up the simulation for a sort of fictitious meteorite fall starting in Broek in Waterland and ending just above the aerospace engineering faculty in Delft, just to see what the consequences would be. Now, to give you a bit of an overview, this is sort of the spread of potential impact points that you would expect from the Broek in Waterland meteorite had it fallen in this particular fictitious scenario. So just, the furthest points apart, it's almost 24 kilometers. But you can see the blue points, those are the ones that are being used very frequently in literature as assumptions in terms of shape and drag properties, and then the average value fits within that. So there's, depending on the actual values that you plug into your model, you can see there's a very large spread in potential impact points. So it really matters what we put in a model to understand how it falls towards the ground. Now, to wrap up a little bit, some concluding remarks. Experimentally, we can actually, use these 3D models that we can generate at very high precision to generate these test articles to perform wind tunnel experiments and actually get a value that matches the actual object for these dark flight models. We did find that these effects are there, so there are definitely influences that are something that we should take into account in our modeling efforts, especially when we have breakup events and we end up with these sort of irregular shaped, asymmetrical meteorites, then you can for sure expect that there are deviations in the strewn field. But of course, everything, the proof of the pudding is in the eating, I think is the saying. It would be very nice as soon as we have a meteorite fall and we have the meteorites that we can actually generate the 3D models, print them in 3D, put them in the wind tunnel, and see what the properties are to sort of reverse engineer sort of the dark flight modeling to see how well those models sort of line up with the actual properties of the meteorite. Now, with that perspective, I'd like to wrap up this talk. So I hope that you know how to fall, and thank you very much.